this lecture, we will try to understand some aspects related to structure and photochemistry of the Earth's ionosphere. In last few lectures, we have defined what is ionosphere, and we have studied various processes which lead to the formation of ionosphere, and we also learned what are the constituents of the ionosphere and how is it different from the neutral atmosphere, and more importantly, which part of the solar radiation is responsible for the creation of ionosphere. So, in continuation to that, in this lecture we will try to understand how does the ionosphere look like. When I say the electron density is equal to the ion density, how many number of electrons are we talking about, and does the entire ionosphere contain the same number of electrons with respect to height, starting from 70 kilometers all the way up to 400 kilometers? What physical or chemical or photochemical processes are responsible for the creation of ionosphere, or for the existence of ionosphere, or for the persistence of ionosphere, right? So, moving on. So, when I say ionosphere, this is how it looks like. So, you can start ideally from, let us say, 60, 70 kilometers, and this figure shows the electron density on the x axis in per centimeter cube, which means for a unit volume of 1 cc, the number of electrons which will be there are given on the x axis, and on the y axis you have the altitude information. So, what you can see from this figure is that the number of electrons per unit volume is not constant throughout, it is changing. It is changing in the sense, as you move from the surface or from the 60 kilometers altitude, the number of electrons will keep increasing. You see this, it is increasing with respect to the height. As you are moving up, it is increasing with respect to height. It is reaching a maximum value here at E. Then there is a steep increase within larger values of altitude. The increase is not much. Okay. Then there is again an increase. Of course, it is all the way increase, and then it reaches a value of higher value, and then it reaches the highest value at approximately, let us say, 250 or 300 kilometers, and then subsequently after that the electron density will decrease. Now, you must be wondering what are all these other lines. So, the dark line to the extreme right is the ionosphere during the daytime and corresponding to sunspot maximum. Okay. And the dark line here is during the night time corresponding to sunspot maximum. So, both of these are solar maxima, so related to the sun's activity, and the dashed lines are the ones corresponding to solar minima. This is for the daytime solar minima, and this is for the nighttime solar minima. So, what you can understand is the electron density is continuously changing with respect to height, and it is also changing, or it has some variability over the period of 11 years or the solar cycle. So, when we already know from very initial discussions about the sun and solar activity that are the number of sunspots on the visible disk keeps changing over the period of 11 years, it reaches a maximum, subsequently it will go towards a minimum, and then again after a certain period of time it will again go to the maximum. That is what I am talking about, the variability. So, even if you talk about sunspot maximum to sunspot minimum, the number of electrons, you see these two values are not same. For example, if you take any given altitude, you take the altitude of peak electron density, which is the peak of F2. Okay. So, this is the peak. So, here if you draw an intercept onto the x axis, it is somewhat greater than 10 to the power of 6 electrons per centimeter cube, right? And you take the same for during the sunspot minimum during the daytime, you take an intercept, the approximate value is slightly greater than 10 to the power of 5 electrons per centimeter cube, which means there is an order of magnitude difference in the number of electrons. Both of them are during the day. Now, this variability or this difference is because of the solar cycle. So that means when sun is very active, you will get more ionization, resulting in the formation of more number of electrons or ions, right? And that means the electron density. The plasma density during solar maximum will be very, very large in comparison to solar minimum, right? That is one important variability. So let us write it down here. One the most important variability is with respect to solar cycle, right? So that is very clear to understand, right? Then the second feature that I want you to understand from this is that day and night. So this is solar maximum day and this is night. So this is the variability that I am talking. Now I am going to draw an intercept right here. So F2. So here also there is a larger difference. See, this is just about 10 to the power of 5 and this is much greater than 10 to the power of 6. So here also there is an order of magnitude difference. That means ionospheric electron density at any given height. So this behavior is common across all altitudes. Wherever you go, the daytime electron densities will be larger in comparison to the nighttime electron densities. So the second variability is that the daytime electron densities are much larger than the nighttime electron densities. So the second variability is called as the diurnal variability, or more importantly we can say day night variability. So can we think of a reason why the electron density is maximum during the daytime and why it is minimum during the nighttime? The obvious reason is because of the direct sunlight. You have the sun and you have the earth. So this is the day and this is the night. So because of the direct sunlight, you have the entire atmosphere in the daytime is getting solar extreme ultraviolet X-rays and ultraviolet radiation, which are creating electron and positive ions, right? So it's obvious that during the daytime there is more radiation. Of course, only during the daytime there is radiation, right? During the nighttime there is no direct sunlight. So during the daytime there is radiation which is creating electrons and ions, hence the electron density is maximum. But you must be wondering, if during the night time, if there is no sunlight, of course there is no sunlight because this is the night, there is no sunlight, and we know it for a fact that ionosphere is created by the solar radiation, or when solar radiation ionizes the atmospheric species, ionization results in the formation of ionosphere. So now the obvious question which should have come in your thought is that during the night time there is no sunlight. So why there is ionosphere during the night time? Why? I mean, this is even if you take this curve, it means any intercept at any height onto the x-axis will give you positive values of electron density, which are not very, very small, which are of the order of 10 to the power of 3, 10 to the power of 4 electrons per unit volume. So what is responsible? What is creating these ions? Why these ions are created even when there is no sunlight? Okay, that is an obvious question, right? Now the answer to that question is not very straightforward. There are now that is where we are going to look at the photochemistry or different chemical processes which are responsible for the existence of ionosphere or the persistence of ionosphere during the night time. Right. Now, second variability is diurnal variability or day-night variability, which means ionosphere's electron densities are highest during the daytime and they are lowest in the night time. Right. So this is the most important curve. And then the third aspect that I want you to understand from this figure alone is that you see the ionospheric electron density is not monotonously changing with respect to height. Either it is not monotonously increasing or it is not monotonously decreasing. So initially it increases up to a certain altitude, it keeps on increasing and then it decreases. So here there is, let's say here there is maximum number of electron density. So electron density is increasing up to this point and then it is decreasing, right? So there should be some explanation which should tell us why electron density cannot keep increasing with respect to height. Why would you expect that? Because the available photons, energetic photons which can cause ionization, is more at higher altitudes, right? As it travels towards the lower altitudes, this radiation or the energy is spent. How is it spent? It is spent in creating the electrons and ions, right? So, if we do not think about all the aspects, we can simply say that if there is more radiation in the upper atmosphere, why do not we expect more ions or electrons to be present in the upper atmosphere, right? So, it is an obvious, seems logical, but it is not like that. So, ionospheric electron density starts to decrease after certain point of time. So, we can say the third important variability is electron density. I am writing within square bracket E, which means electron density versus height is not monotonous, which means it is neither increasing nor decreasing, right? And then the fourth important aspect that I want you to understand from this figure is that I have marked these regions as D, E, F1 and F2. You see there is a small change in the slope here, right? So, we are calling it as D, then E, then F1 and then F2, right? So, these are similar to what we have seen in the neutral atmosphere, small variations in the slope or the direction of slope. We are calling them as layers. So, these D, E, F1 and F2 we call it as D, E, F1 and F2. What are these? These are called as the layers or regions of ionosphere. These are called as various different layers or regions of the ionosphere. All right. So, we have 4 regions of ionosphere during the daytime, and when you see during the night time, there are only 2 regions, E and F. What happened to D? It has disappeared. What happened to F1? It has also disappeared. So, these are the layers of ionosphere during the daytime, and during the night time only what survives is the E and F layers only remain or survive by the time of night, right? Now, at this point of time, we are able to grasp the basic structure of ionosphere, like how it varies between the solar cycles. If I ask, when do you expect the maximum amount of electron density to be present in the ionosphere? You would obviously say it will be during the day of a solar maximum year, you will find the maximum number of electrons per unit volume. Does it vary with respect to time of the day? Yes, it does. During the mid afternoons or during the daytimes, the electron density will be at its highest value, and during the night time, it will be at the lowest value. So, does it increase or decrease monotonously starting from the surface, starting from the 70 kilometers altitude? No, it increases initially and then it decreases as you are moving from the ground towards the space, right? So, these are basic aspects about the fundamental structure of the Earth's ionosphere. By the time we realize these simple aspects about ionosphere, we already have a lot of questions. We already have a lot of unknown things within this small figure. What number one, the first question should be, why the ionosphere should exist at first to begin with in the night time? Because there is no direct sunlight, there is no reason for ionization to happen, right? Now, in order to understand that, we should introduce something, we should introduce a simple term or simple process which is called as recombination. So, name itself is very indicative of what it may actually mean. Recombination. Recombination is something which is exactly opposite to ionization. You know what is ionization, right? Ionization is the process of creating electrons and ions, or the process of removing electron from a neutral atom from the outermost orbit and creating a free electron and a free ion, right? Now, exactly opposite to this is called as recombination. So, if you say X is any species plus H nu giving you X plus electron, the opposite is X plus electron gives you the neutral species. That is it. This is the recombination, right? Now, these two species, the ion and the electron, are not stable. So, it is obvious that they will try to recombine and give back the most stable form, which is the neutral species. Right? So, here we must understand, as long as there is sun, there is direct sunlight, it is continuously creating electrons and ions. Just because these are not stable species, they will recombine and form neutral species. So, this process of creation of electrons and ions and this recombination again creating the neutral species is a continuous process in which electrons are simultaneously created and they are lost by the process of recombination. Right. So, if I add this puzzle, then the question would be, let me frame it. The question would be, the solar radiation is there, it is creating electrons and ions, it is recombining. This process can only sustain as long as the sun is there, as long as it is the daytime. So, daytime you can understand a lot of electrons are created, they are immediately recombining and forming the neutral species. Now, you take out the sun from this picture, what will happen? So, all the electrons and ions which have been produced in the presence of sun must recombine and form neutral species. So, we would ideally expect during the daytime the electron density is there, and during the night time gone, nothing. Only neutral species are there in the entirety of the Earth's atmosphere, let us say 400, 600 or 800 kilometers. But it is not the case. So, for example, if that happens, then we will have to shut down all the long distance radio wave communications during the night time and say that until the sun comes up, we will not resume the communications. Is it so? Is it an actual or realistic scenario that we have today? It is not. So, which means that ionosphere does exist even during the night time in the absence of sun. So, this is the most important question that we are going to answer in terms of actual derivations or simple mathematics, that why the ionosphere will exist in the absence of sun. Okay. So, that is the most important question or most important takeaway from this simple diagram, right. I hope you have understood all the different aspects, what I wanted you to grasp, or what I want you to be very familiar with. Okay. These are the very basics, and your basics should be very, very clear. Yeah, so these are the very basics. Then we will move on and see more interesting aspects about the Earth's ionosphere. So, always remember that this question is a valid question, and in our discussions we are going slightly towards those aspects which will directly answer this question, right. And more importantly, the second most important question I forgot to frame earlier is that why the electron density is not changing or monotonously changing with respect to height. Simple common sense says, as you move towards larger altitude, there is more abundance of energetic photons. So, more ionization should happen, right. So, which is valid, of course, which is what you see as you are moving from here to here, right, up to F2. You can assume that as why the electron density is increasing, because we are moving into higher altitudes where there is more abundance of photons, the electron density is increasing, right. But this is where it fails, or this is where it turns back and says and decreases, right. So, we should also explain why this decrease is happening. Okay. So, just as a starters, what we can see is that available number of photons is increasing with respect to height from in this direction. Rather, if you go in the same direction, the number of neutral species which are available per unit volume is continuously decreasing, because we have to think of the exponential decay of the neutral species with respect to height. So, as you are moving towards the higher altitudes, of course, there is more abundance of energy, but the takers, the neutral species which will actually undergo ionization, is becoming increasingly small, right. The exactly opposite is true for if you go in this direction, right. All right. So, let us define these ionospheric regions. So, this is ionospheric regions. What are those? D, E, F1 and F2. So, this figure simply shows the neutral temperature variation with respect to height. Based on those turning points, you have defined troposphere, stratosphere, mesosphere, thermosphere. Ionosphere is what exists above these altitudes, okay, almost up to 400 kilometers is a reasonable limit for calling 400, 450 kilometers, right. So, this is the ionosphere. When you are talking about ionosphere, this characterization of temperature with respect to height is not important or is not relevant actually. But actually ionosphere will look something like this. Okay. So, what I have taken is, for example, we have taken solar maximum noon time because we have already seen solar maximum is a period of time when there will be maximum number of electrons, and of course noon, direct sunlight, right. So this blue curve shows how the variation of electron density with respect to height looks like. So on the x-axis you have the electron density, the particle density, the charged particle density per unit volume in centimeter cube, and height in kilometers, right. So the bottommost region is called as the D region, D, capital D. Okay. The region which is the region of the Earth's ionosphere, which is sitting immediately above, is called as E region. Okay. And then immediately above that, let's say starting from 150 kilometers, the region is F1, and F2 is the topmost region of the Earth's ionosphere. But F2 region is that where there are maximum number of electrons per unit volume. The total number of electrons per unit volume will be of the order of 10 to the power of 12 electrons per meter cube. So you imagine a cube of each side equal to 1 meter. Within this cube, there will be 10 to the power of 12 electrons, right. So equal to the number of neutrals, equal to the number of ions. Okay. Now, for reference, this yellow curve shows the neutral density variation with respect to height. So at any given, so at the bottommost height, the neutral density is almost 10 to the power of 14 per centimeter cube. You can convert that into meter cube, then you will get a realistic number, which is the number of atoms at STP at the surface. Okay. So what is happening? This is decreasing with respect to height. Okay. So this is decreasing with respect to height. So as you move from the top, the number of neutral species is increasing exponentially as you go towards the surface. Opposite, it is decreasing exponentially. The direction of solar radiation is towards the surface. As the radiation is traveling towards the surface, it is encountering more and more number of neutral species. More and more number of neutral species. Ionization will keep increasing up to a certain point. After that, the photons, since the ionization is constantly happening, the number of photons, which are energetic photons, X-rays, ultraviolet radiation, they are also decreasing because the radiation is traveling towards an optically thick medium, it will attenuate. So the intensity of radiation, I, incoming radiation, because radiation is traveling from the top towards the bottom, I is equals to I naught e to the power of minus mu x. What is mu? Mu is the attenuation coefficient. So as the radiation is moving towards the surface, the intensity of radiation is decreasing exponentially. At the same time, because of the pressure, P is equals to P naught e to the power of minus h by h. Okay. The pressure, or it is equally true in terms of, let's say I said density is decreasing as you go towards the higher altitudes. So density towards the surface is increasing exponentially, right? So you take these two equations, they're exactly opposite to each other. You're traveling towards the surface, the intensity is decreasing and number density is increasing. So because of these two opposite exponential variations, you would naturally expect that there is a balance, or there is certain altitude where these two things will intuitively be equal to each other. So there are equal number of photons and there are enough number of neutral species to take care of all these photons and release maximum number of electrons and ions. That will be the altitude where F2 region will exist, or that will be the altitude where maximum number of electrons will be present. Okay. So this was some discussion about the basic structure of the Earth's ionosphere, and most importantly about the variability of ionosphere. We have defined what is ionosphere, we have seen how does it look like, and third most important aspect is, does it vary, does it change with respect to time, right? We realize it does in different ways. Okay. So we will continue our discussion with more interesting aspects about the Earth's ionosphere.